You know, in today's industries, having consistent power isn't just a nice to have, it's the absolute foundation of everything. But what happens when that foundation is shaky? What do you do when the grid can just vanish, threatening to take your entire operation down with it? Well, we're about to look at a seriously high-tech answer to that exact problem, engineered by a global leader in this space, Starcharge.
So let's head to Ethiopia. It's a place that's growing fast, but like a lot of places, its power grid is feeling the strain. This means frequent, totally unpredictable outages. And for any industrial business there, this isn't just some small inconvenience. No, it's a constant threat and honestly, a major roadblock to growth.
And that really makes you wonder, right? It's so easy to think of a blackout as just, a bit of lost time. But the actual cost? It's so much deeper than that. It's really a domino effect of problems that hits the bottom line, and it hits it hard.
And here's how that cost breaks down. First, you're talking about really sensitive, expensive machinery getting fried by sudden power cuts or voltage dips. Then, your production lines stop dead in their tracks, which means wasted materials and products that have to be either thrown out or completely reworked. And on top of all that, there's the massive expense of the downtime itself and the complicated, pricey process of getting everything started again. It all just adds up to a huge financial risk.
This is exactly why a standard backup generator, the kind that rumbles to life after a few seconds, just won't cut it. By the time it kicks in, the damage is already done. To actually prevent these failures, the switch to a backup power source has to be so ridiculously fast that the equipment on the factory floor doesn't even notice it happened. It has to be seamless, totally instantaneous.
And that incredible need for speed brings us to the core challenge of this whole project. It's a single, super demanding requirement that basically defines every single part of this solution.
Just look at that number, less than 20 milliseconds. Okay, for perspective, it takes you about 300 to 400 milliseconds to blink your eye. This system has to sense a grid failure and switch to its own power more than 10 times faster than you can blink. That's not a goal. That is the absolute non-negotiable mandate.
Now, to pull off that 20 millisecond switch, a whole list of tough technical specs had to be met. The system needed to handle a high-voltage 33 kilovolt grid. It absolutely required a special piece of gear called a static transfer switch. And crucially, it needed to have enough juice. We're talking over 1,700 kilowatts of power and over 4,100 kilowatt hours of storage to keep an entire industrial plant humming along without a hiccup.
So the big question is, how in the world do you build something that can react that fast and that reliably? All right, let's peel back the layers and take a look at the core tech that makes this whole seamless switch a reality.
Okay, so at the very heart of this thing is the energy storage system, or ESS. The easiest way to think about it is like a giant, incredibly smart battery. It's actually made of multiple cabinets all working together, and they use lithium iron phosphate batteries. That's a type known for being really stable and safe, perfect for tough industrial environments. Its whole job is to just sit there, full of energy, ready to unleash it in an instant. But how does that power get out in under 20 milliseconds? Well, the magic happens right here, with this thing called the static transfer switch, or STS. This is the hero of the story. This tough, IP54 rated box is constantly watching the grid. The very instant it sniffs out an instability or a failure, it makes that ultra-fast, seamless switch from the grid to the battery power. It's the critical, lightning-fast gatekeeper of the whole operation.
And of course, something has to coordinate this whole ballet. That's the job of what the source material brilliantly calls the control brain, the Microgrids Central Controller, or MCC. This is the intelligence layer that's managing the batteries, the solar panels, the factory's power needs, and it's the thing that tells that all-important STS exactly when to make its move.
And this brain is truly built for the job. It's incredibly fast, using a special multi-core architecture for that split-second reaction time. It's stable, handling not just the seamless switch, but also the ability to restart the entire facility's power from nothing, a critical feature called a black start. And maybe most importantly, it's resilient. It has dual server backups built right in, so you know it's always on and always ready.
But here's what's really cool. This intelligent system isn't just a one-trick pony. It actually operates with two completely different game plans, and it all depends on one simple question. Is the main power grid on, or is it off?
Okay, so when the grid is up and running, the system's whole philosophy is about being efficient and getting prepared. It uses any available solar power first, then stores any extra energy in the battery, always keeping a healthy reserve just in case. But the second the grid fails and it goes into what's called islanded mode, the philosophy flips completely.
The priority shifts to survival. The battery system itself actually creates its own stable internal power grid. It becomes grid forming, all to keep the critical machines running for as long as it possibly can.
And the best part? Nobody has to flip a switch. This change in strategy is completely automatic. It's all handled by a smart, layered system that coordinates everything from the cloud to the local controllers. It automatically detects the grid failure and seamlessly shifts its entire game plan to match the new reality, all without a single person having to do a thing.
So you've got this incredibly fast, super intelligent, and really adaptable system. What does that all actually add up to? What's the real-world impact? What's the ultimate payoff for the business?
Well, the benefits circle right back to the exact problems we talked about at the beginning. Downtime and wasted materials? Drastically reduced. The equipment is now protected from those damaging power surges, which means it runs better and lasts longer. And because the system is always trying to use its own solar power first, it actually lowers the company's energy bills. It basically takes grid instability, a constant threat, and turns it into a complete non-issue.
And hey, this isn't just theory. The source material gives us case studies from really similar projects that show the financial impact is real. We're looking at annual savings in the millions of Chinese yuan, which can be hundreds of thousands, even millions of dollars, all from putting these kinds of smart energy solutions in place. The numbers speak for themselves.
So at the end of the day, this solution isn't just about surviving that first 20 milliseconds of an outage. It's about long-term resilience. The system is designed with enough energy stored up to run the whole facility for a good long while. Some versions can guarantee over 2 hours of backup, even at full power. It provides genuine energy independence right when you need it most.
And that really brings us to the big picture. This project in Ethiopia is a powerful answer to a local problem, for sure. But as power grids all over the world face more and more challenges, from aging infrastructure, crazy weather, and just rising demand, it leaves you with a final thought. Is this kind of fast, intelligent, self-sufficient microgrid the new blueprint for how all of our critical industries are going to power themselves in the future?